Hi! We'll now be closing Module 7, Introduction to Renewable Energy Analytics, with this third block. In this third block, we'll look at the various types of forecasting products from a conceptual and a more mathematical point of view. But first of all, we need to introduce the setup for forecasting. It may sound stupid or a bit funny, but forecasting is about the future. So that means we need a clear reference point that defines where we are now, what is the past, and what is the future. When doing that, normally we say we are at a given time t. Let's say it's 11 in the morning and you have to place offers in the markets. You use this forecast for the day after. And then you're interested in what happens for several time t plus k in the future. K is called the lead time. T plus 1, so k equal 1, means that you predict one step ahead. If the resolution is hourly, it means you predict 1 hour ahead. If you still have an hourly resolution and you predict for tomorrow at the same day, you say t plus 24. So thinking of future lead times, you may be interested in looking at what happens tomorrow, for instance, between noon and 1 in the afternoon, because you have to place an offer for an energy block there that you will generate from your solar power plant or from your wind farm. We use a notation as big Y, uppercase Y, t plus k for the random variable power generation at time t plus k. So fundamentally what we're saying here is that this production has a random component, and we will want to characterize it through our forecast procedure. A forecast, conceptually, is an estimate for time t plus k, but given time t, of some of the characteristics of yt plus k. We'll look afterwards in terms of forecasting product. Maybe you will want to describe the mean of this random variable. You may want to describe some quantiles, some intervals, or the full distribution for this random variable. Also, I said given time t. Given time t means it's conditional to the information we have at that time. We explained in a previous block, up to that time we can have a lot of power measurements. We may have a lot of meteorological measurements, remote sensing measurements. But only up to that time. Obviously, we don't have measurements about what's going to happen in the future. Though we may already get forecasts for the future that are weather forecasts. So we may have information in terms of measurement for this window, and then we may have information available at time t that are weather forecasts, so for this window. Now in terms of notation, since a forecast is an estimate, in statistics we'll use a little hat on top of variables to tell their estimates. So we'll use hat as a notation for forecast. And to reflect this idea that we look at time t plus k given information up to time t, we write t plus k, the symbol of given in probability, and then t. Now for illustration, I will use a dataset for Western Denmark. Energinet is the system operator for Denmark and has responsibility for all this area. All the small wind turbines in gray you see around here are connection points for wind turbines that are spread all over Western Denmark. There are approximately 400 of these connection points. They are called trafo stations, and we have data for all these locations for many years. And the overall capacity for the period was of around 2.5 gigawatts. So the data is not the most recent one. For operation purposes, there are control areas that are defined by Energinet. Here in this dataset, there are 15 of these control areas. So one may already aggregate wind power generation for each and every of these control area. And here, to make it even simpler, we've decided to have only 5 zones that are also aggregating these control areas. The zone 1 that aggregates the control areas 1 to 3. So this would be the aggregated zone 1. the zone 2 that gathers control area 5, 6, 7, here, etc., etc. We'll use this data and forecast for these areas as illustration for the various concepts we'll discuss in the following. The first type of forecast, which you must have seen before, at least through the previous modules, is what we call a point forecast. And a point forecast will give a single value for power generation, being for wind farm or solar power plant, if you look at this type of assets, a single value per lead time of interest in the future. Let's say here we have an example of a forecast. The forecast is issued at time t that we're going to look at time 0, and then all these values here at the bottom are the lead times. So think of t plus 1, t plus 6, t plus 12, etc. These forecasts here look like a smooth curve, but obviously in practice you have a certain resolution. These forecasts here are hourly, so 1 value per hour, so you could see it as the average power generation for the hour preceding the time you look at. And then these bubbles, these small circles, are the measurements that we got a posteriori, and we compare the observations with the forecast. By expressing a single value for each and every lead time in the future, what is the statement we're making? If you think deterministically, you say, I'm telling you what's going to happen. This is going to be the power generation for this lead time. The power generation, here expressed in gigawatt, the power generation for t plus 12 is going to be 0.6 gigawatt. Actually, if you think of it, and if you look at power generation, renewable power generation, as a random variable, as a stochastic process, the statement you're making with a point forecast is that you're making a forecast of the expectation of that random variable, so the average, you could say, of what could happen, given your information set, gamma, a model that you've used for forecasting, and then eventually a set of parameters that you've learned. So a point forecast that is given by a single value, like here for each and every lead time, should not just be seen as, I'm sure this is what's going to happen. Actually, it is the average of what I think is going to happen. If we were to issue point forecasts for these various areas, we have the 5 zones that we've defined before, zone 1, 2, 3, 4, 5. You see that we have these single trajectories for each and every zone. We can compare them to observation a posteriori. And then, since these zones are actually next to each other, there is some similarities in the pattern, so the development of wind power generation will be quite similar, even though there are going to be some local effect, there are going to be some time delays if the weather fronts are moving, for instance, from west to east, so that will impact the shape of this forecast. These 5 plots are for a given time, for the following 40-something lead times, and for the 5 areas that we defined for Western Denmark. Now, we discussed in a previous module quantiles. We explained that quantiles are related to a certain nominal level, so you could see it as a probability level, and for this given probability level, we have to go through the cumulative distribution function to see what is the level of power corresponding to this nominal level. Formally, when defining a quantile and a quantile forecast, the statement we are making is that we believe that if predicting this power value, we believe there's a probability alpha that what we will observe is going to be below or equal to this quantile value. If you say alpha is equal to 0.1, you think that power has a chance of 10%, the power observation has a chance of 10% to lie below this value. If you say alpha is 0.5, like in this plot, you see here the bold line is a quantile forecast with alpha equal to 0.5. So that means in practice, we believe there's 50% chance that what we will observe is below, and so 50% chance that what we'll observe is above. If you compare with the point forecast we got from before, which is here with a dashed line, you see that they can be very close. Actually here, they overlap. If you were to analyze the distribution of errors or the distribution of the random variable power generation originally, you see that if distributions are symmetric, the median, so the quantile with nominal level 0.5, will be equal or close to the mean. And we said that point forecasts are the mean, the expectation of what could happen. The quantile forecast here in this case is very close to the mean because we have this nominal level of 0.5. Now let's try to think of what we said. The point forecast is a statement about what we believe could happen on average, so over the potential realization for the random variable. Now we have a quantile forecast that's telling that we believe there's a certain probability, so here 0.5, that what's going to happen, what we're going to observe in terms of power generation is going to be below, and 50% that what's going to happen is going to be above. Both of them don't seem really informative. The average of what could happen, and now there's 50% chance is going to be below, 50% chance is going to be above. But actually, if you were to define several quantile forecasts that will define a bound of an interval, then you could get very interesting information about the future renewable power generation. Imagine here in this example plot that we define this quantile forecast that would be the bound below with a probability or nominal level of 0.05. So there's only 5% chance that what could be observed in terms of power generation is below this bound. On the other side, you have a quantile forecast with a nominal level of 0.95. So there's only 5% chance that what will be observed will be above this line. So that means eventually that you have this envelope here, your forecast takes the form of an envelope, and you know or you state there's a 90% chance that whatever you're going to observe is going to be within this envelope. You can imagine it's quite interesting. If you have a very tight envelope and you say you're very sure that it's going to be within this envelope, it's very powerful information. If you have a very broad envelope and you say you're not so sure that it's going to be within this range, then it shows that the forecasts are fundamentally uncertain. In this case here in plus, we have gotten all these observations afterwards, and you see that it seems that on average we have actually 90% of the observations within this envelope. So formally here, this kind of envelope are defined by interval forecasts, because if you look at each and every lead time, you actually have an interval with a lower bound, a quantile forecast with the nominal level here, for instance, of 0.05, and the upper bound is another quantile forecast here, for instance, with the nominal level of 0.95. These interval forecasts are interesting forecasting product, because they give a powerful information, but you can also see by yourself it's very visual. So the decision maker can really have a feeling for what's going on and the quality of the information is being given. Eventually, if we were to define a lot of this interval forecast, so each and every of the intervals would have a different nominal coverage rate, this nominal coverage rate being the difference between the nominal levels of the two quantiles that define its bounds. So it could be 10%, for instance, it could be 20%, or it could be 90%, as we had in the previous example. So we are looking at the same plot here with probabilistic forecasts, but now instead of having a single interval, we have a lot of intervals with different nominal coverage rate. We recognize the same interval as before, which is the widest one, and it has a nominal coverage rate of 90%. We state there's a 90% chance that whatever is going to be observed is going to be within this envelope. But then we've defined some other envelopes, and the next one has a nominal coverage rate of 80%. So we have a tighter range of possibilities, but we also have a lower confidence, if you want, than what we're going to observe is going to be within this range. And then one can continue with tighter envelopes down to a 10% nominal coverage rate. If you think of it, we're actually here fully describing the random variables of interest, because all these interval forecasts that define this nice plot are composed by different quantiles with different nominal levels. If you start having different quantiles with different nominal levels, you can actually take a slice and fully draw the cumulative distribution function for that random variable of interest. This is an example here when you have in the x-axis power, so in gigawatts, and here you have probability. And by looking at the value of the different quantiles, the first one is at nominal level 0.05. So here for the nominal level of 0.05, I have this power value, and this defines 1 point of the cumulative distribution function. Then I look at the next quantile with nominal level 0.1. So at 0.1 here, I have the next power value, etc., etc. 0.2, this value, 0.4, this value. So we can reconstruct the cumulative distribution function. These are, you would think, the most advanced and general products we can define if we want to describe what is going to happen, but also what are the uncertainty involved. Actually, when we describe this forecast, we are not looking at all the information that we may need for decision making. These are examples of probabilistic forecasts for the 5 zones we have of interest. And again, you can see there is similarities in the trend, there is similarities in the uncertainty level. In some periods, the uncertainty is higher, and this seems to be the case in the various areas. Sometimes the uncertainty is lower, but still, do we know, for instance, about the dependencies between the areas? Do we have any information about how correlated the forecast errors may be? We don't, not with this kind of representation. Let me explain that. Look at a certain wind farm. Actually, here the data is from a wind farm in the south of France, near Montpellier. And let's say I would issue probabilistic forecast in the form I showed before with all these nice envelopes with different shading. And now I will generate some trajectories in the future that would respect this probabilistic information, but just you're going to consider a different type of correlation pattern in time. So you might have totally uncorrelated trajectory in time, so the correlation between time t and time t plus 1 is none, it's 0. We generate trajectories that respect the probabilistic forecast envelopes, but have a correlation of 0 in time. This is the type of trajectories we would see. Gray, it's just all over the place. And in red, by the way, this would be the observation collected for this period of 3 days that we are looking at. And so if you were to compare your forecast in terms of a lot of trajectories, you see that the correlation structure does not really mimic the nice pattern we see in the observations here in red. If I do the same thing, I use the same forecast envelope, the same probabilistic forecast, but now I try to model the correlation that there may be in time. So I will issue trajectories. So you have this nice spaghetti plot with a lot of trajectories. If we look at these trajectories one by one, they will have some type of temporal structure. Here there's no type of temporal structure. It's just going up and down all the time. It's white noise within some type of envelope. Here we have this correlation structure, and we can actually verify that we can model correlation structures that will mimic also the correlation structure we'll observe in observation. So, on top of having information that are the marginals, this probabilistic forecast that we saw before, we may also want to model the correlation structure that can be in time, that can be in space, and then this type of trajectory will be able to represent both of them, the probabilistic forecast information in terms of marginals, and then the correlation structure. In practice, this is how we would look at it. You have a forecast as we saw before. So this would be a forecast here in bold, the point forecast, and the observation as we had before, same example. We have also a set of trajectories, also called scenarios, that are around the point forecast. And the point of these scenarios is to mimic the information given by the probabilistic forecast. So you see here the uncertainty around the point forecast is represented by how these scenarios develop. But then also these scenarios have the information in terms of the correlation structure or how smooth we believe somehow the power production to be over the following hours. The process to generate these trajectories or these scenarios is very complex, but still today it is actually the most advanced product that can be issued for a wide range of forecast users. Then they may be able to plug them in different type of decision-making processes where information on uncertainty and correlation can be of particular importance. You may think of the coordinated operation of some storage devices where we need to know about uncertainty and correlation between different locations, but there might be a lot of other problems. Here would be some representation for the 5 areas of Denmark that we've been looking at. This is for the same period as before. Now, instead of looking at this probabilistic forecast in terms of envelopes with different type of nominal coverage rates, we have a set of scenarios that give you some alternative futures. I tell you, I believe on average, this bold line is what's going to happen, a bold line for each and every zone. But then if you were to think of alternative future, you may pick one of these scenarios and say, oh, this is an alternative future. You pick another scenario, oh, it's another alternative future. And you can plug that into decision-making processes where you try to be robust versus any type of potential realization in the future. Finally, some of you, if you dig a bit more into this field, or if you do decision-making based on forecast, some of you may see new products that are not like those that I defined before. So for instance, some have been interested to filter the forecast information because too much information in the forecast can be overwhelming, and then you can have user-defined events. So let's say, for instance, that some are interested in the ramps, so in a steep increase in power generation. Instead of predicting all these nice envelopes, instead of predicting all these alternative trajectories in the future that can be quite too much information, maybe you say, please just inform me about the probability of this event I define to happen. So some type of events would be ramps. So tell me what is the probability we're going to observe some steep increase in power generation. In the very beginning of this course, we discussed the duck curve. System operators like that in California are worried about steep increase in power generation when the sun is peaking up, decrease in power generation when the sun is peaking down. Then there might be some worries about high variability events. Here the curves seem very smooth, but what if the power generation would fluctuate a lot suddenly? Then you will need very flexible units to compensate for that. So you may want to know what's the probability of this to happen. Thank you very much. Now I would like to invite you to use the self-assessment quiz to check your understanding.